Okay, thanks for coming either into the room or online. Today is the third lecture. We are going to go into the logic, which will be much more technical than the last two. That's why we have a whiteboard here. Let's hope it works fine. So after the first two lectures, you already know what I want to do in your research project. We want to build intelligent system in the sense that it adapts to the environment, even though it still always have, in general, insufficient knowledge and resource. And we want to build that system in the framework of a reasoning system, following a logic. So that's the logic we are talking about. That's called non-axiomatic logic, or NAL. So what a logic means, actually, I mentioned that last lecture. Usually when we say we have a logic system, we mean three things. You need to specify a formal language or accurately defined language to represent your premise and conclusion and so on. And you need a set of inference rules to derive new knowledge from given one. And also you need a semantic theory to define the meaning of words and the truth of sentence and so on. Actually, last week we have already discussed the semantic part, and I explained what I mean by truth and by meaning according to given experience of the system. So today we will focus on the other two parts. That is, we are going to introduce a formal language used in our system and a set of inference rules. So you see, again, this is the issue facing AGI we mentioned in the first lecture. So we're talking about we really want to do everything that related to what we call intelligence. So it's clearly a very, very big topic. How can you do it? How can you build a system to do all of those? Well, from an engineering point of view, again, you have to do it step by step. Okay, but here I have already criticized the approach of the normal divide and conquer. You do one cognitive function at a time. I claim that it's not going to work, but at least that's not the approach we have been following. But what we are going to do is, again, to build a system step by step, but not according to the cognitive function it carried out. Instead, it's according to the logic it implements. So we are going to start from a very simple logic with very simple grammar and the inference rules. But based on our theoretical assumption about intelligence. Then what? Then we are going to do it layer by layer by add more rules into the system to make it more and more functional or more and more powerful. So that's the basic approach. And also, even at each layer, we will actually build two logic. First one is the idealized version, which will do the reasoning, but without the restriction of insufficient knowledge and resource. So we are going to do it in an idealized situation where we assume we know everything, we have all the time and space needed. So then we are going to do an extension or modification of that idealized form and to make it real, what we call a non-axiomatic logic. Okay, so that's the big picture summarized in this diagram. Okay, you'll see that in theory, there are 9 layers, which we are going to introduce one by one. And today, actually, we will only talk about the bottom layer, the first level. Okay, and the others we are going to talk about it in the next, in the coming lectures. And those 9 layers can be further divided into 4 groups, which we will talk about in the future. Now it doesn't need to make sense to you. Okay, and also you see each layer we are going to start with the idealized version, which is called inheritance logic. Then we will extend it that into what we call a non-axiomatic logic. And eventually, what is really in our code is this part. is the non-axiomatic logic part, and also all the layers are actually tangled together in the implementation. So this structure is more like the conceptual structure I use for education purpose, so that I don't have to overload you with all the information altogether. And also, this is also more or less how I develop this system over time. So that's not exactly, but roughly that's the order I follow. So now we will start from the very beginning. So you build a logic. What is the best known logic? I assume everyone in this class already learned first order predicate calculus in your college time. Okay, and most people call that classical logic and use it as the most standard version of logic. But actually speaking, in the tradition of logic history, there are actually two different schools, two major schools of logic. You may have heard about them. One is now what we call mathematical logic. The other one in textbook is called traditional logic. As the name suggests, it's taken to be, in history, but it's already out of date. Okay, or technically speaking, the traditional logic is also called term logic. And here I have a link in that people can look at the Wikipedia page as well as other material, which introduce more about this term logic. Predicate logic, I assume you already know. Okay? But for today's lecture, I will only give you a very brief summary about what's the difference. And why I talk about this, of course, you can guess, because I'm actually using term logic. Okay? Even though the current popular version of almost everyone use is the mathematical logic tradition or predicate logic. The founder of term logic or traditional formal logic, everyone knows is Aristotle. And mathematical logic is Frege and Russell and Whitehead. And a major difference between the two, which is very often omitted in the discussion when they're compared, is that they are actually not thinking about the same thing. Aristotle's logic, we can say, is about everyday thinking, or is about thinking and reasoning in general. He is focused on, how we do inference, how we communicate, how we argue with each other, and so on. Okay, in a general sense. When mathematical logic starts, as the name suggests, it's very clear it's about mathematics. Even though some people think that doesn't matter because mathematics provide us with the purest or the best case for reasoning. So that's why many people say that difference doesn't matter. But later you will see, I'm going to strongly argue, these two target domains are completely different. They demand different logic. So that's why I go back to Aristotle in a certain sense. So mathematical logic is called mathematical logic, I think, for two reasons. One is it's a form. It's similar to mathematics. It's fully formalized. But another thing is about the content. It's really about the reasoning we do when we prove theorems in math. Okay. And that is part of everyday thinking, but not the full story. And actually later I will argue that when we reason outside mathematics, the rule we use are actually different from the rule we use when we prove theorems. Okay, so that's a fundamental difference to me. And then technical, how to write your formula or a sentence or a proposition, what do you call it? There is a major difference in these two traditions, okay? Which in term logic, there are several different names. One name I have here is to say that every sentence is put in the format of a categorical sentence. What that means? A more familiar name is subject predicate. Okay, so in traditional logic, in term logic, everything is a subject and a predicate. And each of them is called a term. That's where the name term logic comes from. Okay, and between these two, there is a relation which is typically called, traditionally called a copular. Sometimes omitted, but the logically is always there. Otherwise, it doesn't make sense. Okay, you have two terms related to each other. That's the term logic format, the basic format. There are some variations which we will see later. Okay. So, but on the other hand, propositional calculus you're familiar with, the basic format of a simple atomic proposition is this. Okay, which take a functional format. That's why it's called mathematical logic. That's another reason. Okay, just like a function. And this is called a predicate. These are the arguments which can be either a constant or a variable. Okay, I assume you're familiar with this, so I'm not going to go into detail. But you can see clearly this format and this format are very different. But of course, most of the current textbook will tell you this is a special case of this because we can take the formula copular as a predicate and this two as two arguments. So we can put this into this. So Aristotle logic is a subset of predicate calculus, okay? Which in a sense is true, but it's not completely true. Okay, and hopefully we will have time to discuss about that. But basically, this is the difference I'm talking about here. That's the format, how to write your knowledge. And then inference. Even if you haven't probably not really have learned Aristotle logic in detail, and bet you heard about this, that Aristotle logic is syllogistic. All the basic reasoning is a syllogistic reasoning or syllogism, which is kind of like, you'll see, if every sentence is a subject and a predicate, then you can have a sentence which is between A and B. You can have another one which is between B and C. Then from that, you derive one between A and C. That's the very basic or the simplified version of what we call syllogistic reasoning or inference rule, whatever you call it, which has the property that each sentence is subject predicate. And in the whole pattern, there are three terms involved. And one of them is a common term between the two premises. Okay? So traditionally, actually, this is called M, the middle term. And we can call this S and P. Again, is subject and predicate. So intuitively speaking, syllogistic reasoning tell you that this relation and this relation can give you this relation with this middle term is an intermediate step. But of course, the order is not always this order, and there may be some additional information associated with the copular, like whether it's affirmative or negative, or whether it's for all or for some. That's the detail. Okay, but this is basically the picture of syllogistic reasoning. On the other hand, in fourth order predicate calculus, the basic form of reasoning comes from propositional logic. We know is nothing but truth table. Okay, so what you have in this case is you have something like, for example, you have truth value for P, you have truth value for Q, which can be true or false, and all possible combination. And based on that, you can define the truth value for P and Q, P or Q, especially you have the truth value of P implies Q defined, all according to different truth value combination. Okay, so this clearly is very different from this one. And also some people argued I can translate this into this format. Yes, it can be done, but there is still some fundamental difference. Later we will talk about. So hopefully that gives you a basic idea about these two types of logic. And every current textbook in logic will tell you, and this is limited only of historical value, and this is more advanced, cover the previous one as a subset. Okay, so that is why almost nobody is actually building their work on term logic in today's research, except a few exceptions, including our system. Okay. Which I will explain why we do that. Actually, the truth is I didn't make that decision at the very beginning, say I like Aristotle better than for some other predicate covers. No, I'm actually going through a different way. Actually, I start with set theory. I'm using set theory for knowledge representation. It just after a while, I developed something which is different from set theory. Then I realized that what I want is actually pretty close to Aristotle. Okay, now I begin to put my system into that tradition, and but of course not exactly the same. Okay, so that's the first difference, and people will notice when you compare my work with other reasoning systems. It's not for solve the predicate calculus. So now you'll see that I will only mention what's our predicate calculus very briefly because you're familiar with it. Instead, I'm going to develop order in this picture. You see, as a term logic, as I said, now it will not be a surprise. I said the basic statement in our system has the form of a subject, copular, predicate. Okay, just like this. What is a term? Well, a term is just an internal identifier or a name. In my following examples, I typically use English words, even though it doesn't have to be, it can be anything. It's just an ID, okay? Or you can just say it's a string of characters. Popular, this one we need to say more. Okay? In NARS, actually, later you will see there are 4 copulars. There are fundamental relations between terms, or later you can also say it's between concepts. Okay? There are only 4 of them, or fundamental one. There are a couple of derived ones. The first one I introduced here is what we call inheritance, which is represented as an arrowhead. So you'll see that there is a direction from the subject to the predicate. So this is actually how I write a statement in NARS. Well, of course, here we are talking about is idealized version. That's what we call inheritance logic. Now you can see where the name comes from. Okay, it's from that copular. Its meaning is fully determined by 2 properties, reflexive and transitive, as defined in set theory. Also, I assume you understand what I mean. Reflexive means that for any term, there is a relation to itself. So this is always true, okay? Transitive means that if you have A to B, B to C, then you can derive A to C. As you can guess, when they talk about the syllogistic inference. The intuitive meaning is the subject is a specialization of the predicate, or the predicate is a generalization of the subject. Okay, that's the relation we have seen everywhere, right? But under different name, okay, in different contexts. Actually, you can guess initially this is the subset relation in set theory. And that's where I started from. So examples, you can say water is a type of liquid. You can say raven is a type of bird. Okay, the second one can also be interpreted as raven as a subset of bird. But the first one is not very easy because, you know, water, liquid, you don't have an individual in it, so it's hard to be called a set. That's actually a reason I switch from, I leave set theory terminology because it's a little bit too limited. But the idea remains the same. Okay. And also in AI tradition, this thing is called even though that also only apply to the raven case, not to the water case. But and clearly, this representation, I cannot, not only I can write it a whole bunch of statements, I can also intuitively write it as a graph or a network with the terms nodes and the couplers as links, right? So it just slightly change this a little bit. I can just draw it in this way and say this is S, this is P, okay? And that's, and not only I can do it for one, I can do it for a bunch of them. So in this case, I can just have it as A to B, then B to C. So we will use this to summarize the two statements I read before there. Okay, just different format about the same thing. Then I'm going to introduce the concept of experience, which actually I discussed last week. Can you see that experience is everything the system has as an adaptive system? It's kind of like the history of the system's past, the interaction with the environment. So when I formalize it, the experience of the system is what? It's just the given knowledge. You know, for a reasoning system, you have to start from somewhere, right? So from some given knowledge, no matter where, whether it's come from a human or it come from your sensory motor or from a knowledge base or whatever, you have to start from somewhere. That's what we call experience in the system, which is nothing but a bunch of statements, or you can write it as a network like that. Okay, it doesn't have to be a connected network. It's just a whole bunch of things that with some relations here or there, and which in the book is called K for, actually initially for knowledge, but later I interpreted it as experience. I use knowledge for something else, which is represented in the book as K star, which is the transitive closure of K, which I'm using terminology in graph theory and set theory. Transitive closure means that everything you can derive from the given network according to the transitivity of this relationship. Okay, so like in this example, I give you, there is a link from A to B, from B to C. Of course, there is also a link from each of them to itself, which you don't need to draw. Okay, and according to the transitivity relation, you can actually derive one from A to C because it's transitive. So this new network is the K star, which is a superset of K, which include both the given and the derived according to transitivity, which is very simple. Now you'll see that starting from this very simple definition, I begin to build the semantics of this simple logic. This inheritance logic you see clearly is still binary. Everything is either true or false. But what is that supposed to mean? Every statement is either true or false. For it to be true, there are two cases. One case is true by definition. That is, every term to itself, by definition, is true because it's reflexive. Another case is true by experience. That is, if this thing is one of K star. You see, it doesn't have to be in K. Okay, as far as it's in K star, that is, either it can be given to you or it can be derived from whatever given to you. So in this case, A to B is true, B to C is true, A to C is true, but the C to A is not true. Okay? If it's not true, it's false. Everything else is false. The truths are given in this true condition. Okay, also pretty obvious. Then we can define meaning of a term. So what is the meaning of a term? The meaning of a term consists of its extension and intension. And these two notions has been used in logic for decades. Here, the meaning I'm using is similar to the traditional usage, but not exactly the same. Okay, but intuitively the same. So you'll see that we can use a graph to show it very intuitively. For a given term, its extension is a set of terms which include all of its non-specialization. What that means? That means everything point to T. Okay, if you have A, B, C, D, of course, they need to be true according to my previous definition of truth. Okay, so all this, of course, including T itself, forms what I call the extension of that term. The intension, as you can guess, is the symmetrical part. Also including itself. So the extension are the more special or concrete terms. Intension are the more general or abstract terms, roughly speaking. Also based on given experience, because experience gave you truth, right? Then from truth, from given truth, you define experience. You can define intention and extension that define the meaning. So this is already very different from the traditional meaning I mentioned last time. The meaning is not what it names in the world in my system. It's its relation with other terms, or is what the system knows about this term at that moment. Okay? Know means that include both its extension and intention, or how it's related to the others. And finally, there is a very simple but a very important theorem that can be trivially proved. That is what? That is, when I say there is a statement from S to P, or with S as the subject and the P as the predicate, what do I mean? That statement is true if and only if in this binary logical context. The extension of the subject is a subset of the extension of the predicate. And if and only if, the intention is the other way around. If you think about the meaning, actually it's pretty obvious. What I'm saying here is, if this is the case, okay, if you have something in its extension, Then by transitivity, of course, this will also be in the extension of this one. Symmetrically, if this is something is intension, then by transitivity, this will also be the intention of this one. That's what the theorem tells you. And that's also for all possible A and B. Okay, that's clearly true, and even trivially true, but it's very important. Why? Because this gave us the way to move from, so far we only have a binary logic, which everything is either true or false, to really a multi-valued logic where truth is a matter of degree. So this actually is an issue that faced by almost all multi-valued logic. On one hand, everyone agrees in many situations, truth is a matter of degree, it's uncertain. You have intermediate points. But on the other hand, it's pretty difficult to accurately specify what that number means. Last time we talked about probability, okay, which is relatively clear. Even though there's still some different interpretation, there's still some debate about when you say probability is 0.3 and what that's supposed to mean. A larger trouble is in some other logic. For example, if you know fuzzy logic, read their book, you will see that they almost never get it very clear what that membership number measures. Okay. They give you some intuitive idea, but that's not clear enough. What this theorem tells us, I'm actually relating this one to a subset relation in set theory, okay? Because extension and intension are both sets. Let's focus on this part. This and this are two sets, okay? And the subset relation in its original form is also a binary relation. Either this one is a subset of this or it's not. But this is very easy to be extended into a multi-value relation. Let's use the familiar Wang diagram, right? If you have this scenario, clearly this is not a subset of this anymore. But you can still say it's sort of or kind of or a subset to a certain degree. In what sense? Because subset is defined as everything here is also here. Okay? In this picture, it's clearly some of the thing here are indeed also in this one, but some others are not. So everyone agreed that in this case, if I want to extend this relation from a binary relation, which is defined in yes, no, into a matter of degree, it's pretty easy. And everyone will do the same at that. Is what? Is to use the intersect part compared with everything you're talking about, okay? So is among everything in this set, what's the percent or ratio, whatever you call it, also in this one. And also this is related to the intuition of probability. And conditional probability also use a similar definition, right? So this gives us the intermediate step we need to turn inheritance logic into a non-axiomatic logic where every sentence is true to a degree. Now I can use this equivalence to define positive and negative evidence for this relation. Okay, now let me draw it slightly differently. Let's say that now we are going to evaluate the truth value of what we call an inheritance statement in now, where the truth value is not binary anymore. Okay. Instead, we have positive evidence and negative evidence for this statement. But I'm seeing this as an extension of the idealized version I just mentioned before. Okay, so I will allow this from 100% true to a certain percent true. Doing that, I'm going to count my evidence here to make things simple. The evidence itself is still represented as an idealized statement. I'm not talking about at this stage, I'm not talking about the evidence itself is a matter of degree. That just makes things too complicated. Okay? So for example, I can say, if I have A, which I know according to my knowledge, which is in a binary form, okay, is both in S and in P. That means as A is in the extension of S and P, which means as far as this one is concerned, it supports this statement. And now you can guess the other part. If I have a B, which is in the intention of both, then that's also positive evidence. On the other hand, if I have something which is in the extension of S, but not in the extension of P, that's negative evidence. That is, as far as C is concerned, this inheritance is not true with respect to this one. Okay? But be careful, since this one is supposed to be multi-valued, or you can think it as a statistical statement. A single piece of counterexample will not just make the whole thing false. It just makes it less true. Okay? With respect to this one, it's not true. And as you can guess, this is something I'm proud of. Okay? Extension and intention is perfectly symmetric in my logic. So everything I can set here, you can guess what happened. If there is something in the intention of P, but not in the intention of S, according to your experience, that's negative evidence. Okay? So that gave us a mechanism where we still use this kind of thing, which belong to this binary logic. We use it to define evidence for this multi-valued logic we are building. Furthermore, I can even simply count the number of this and this. Then I have a numerical, I just say, not just say how many of them are there. I can just simply count how many of them are there as amount of positive and negative evidence, which are nothing but the sense of the common extension and intention and the difference between extension and intention. And be careful, difference, there is order. The order matters, okay? And which will relate to what we covered last time. Last time, what we have done is we assume if we already have a measurement of evidence, then we can define truth value, okay? Let me bring back that slide so that you know what I'm talking about. So this is from the last lecture. Okay? Last time I just said, if I can define a measurement of positive and negative evidence, okay, then I'm going to use the ratio as the frequency, and I'm going to use this ratio as the confidence.
I don't think that people on Zoom see the slides. Or no, yeah, they do on the screen. Okay, yeah, that makes sense. Yeah. Okay, sorry.
Anyway, as far as now they can see it, that's something we covered last time, but we didn't mention where this initial measurement of evidence come from. Okay, that's have to wait until today's lecture. So you'll see that since today we provide what is positive, what is negative, and then what we said last time will give us the actual truth value used in the system, as well as the relationship also I explained last week. Okay. And also you can relate it to probability theory somehow. So that's this. Now let's continue today's lecture. So now again, let's see what we have done. We define a very simple logic, binary, and we use it to define what is called evidence for the one we really want to build. And then from there, we actually define truth value for the sentence. So it will be FC, which are used to summarize this evidence in what in idealized situation. This is also a point where people tend to get confused. Okay, people tend to think, okay, since you define it in this way, that means whenever you want to define, you want to calculate or decide this, you need to count the evidence, and also why, what if these relations are also uncertain themselves? What if the confidence should not be treated as with the same weight? Well, yeah, they're all correct. But what we have here is a definition. Definition means that in idealized situation, how this number is determined. It's not the same as how you actually measure it. It sounds like an excuse, but think about physics. How do we define what is a meter? What is a kilogram? And what all those definitions, if you check the textbook, is defined in a highly idealized situation, which is different from how you actually measure the distance. Okay, you measure the distance using some kind of ruler, but where the ruler come from, the ruler eventually is built according to that idealized definition. Okay, the same story here. So this is give you a way to understand intuitively what this measures. But it doesn't mean we actually get it in this way, just because that's too idealized. So how we actually get it, before we say that, now is the time to summarize the grammar rule of the first level of non-axiomatic logic. You can see it's very simple. Here, the core is what we call a statement, it's just this, okay? If you have a statement plus a truth value, this is what I call a judgment in this literature. Well, you can change a different name. Anyway, I need to make a difference. Okay, statement by itself does not include a truth value, and the truth value, especially in this multi-valued version, the truth value add into a statement to make it a judgment. A judgment is one type of sentence you can put into the system. Another type of sentence is a question. Question is what? Question, intuitively speaking, is a statement without a truth value. It's kind of like I'm asking the system whether this is true or to what degree it is true. Okay, that's the simplest case, or what we call evaluative question, or what in your English class called yes/no question. Okay? Even though in this case, yes/no become a matter of degree. So I'm asking you to find the truth value for me for this given statement. So this is one type. That's the first one. It's kind of like a statement without a truth value. Actually, in implementation, we actually make use a question mark to indicate that's the case. Another type is one of them is missing. It can be this one or it can be this one. In our implementation, of course, we also gave it a name, not just a question mark, but that's the idea. So this question is asking the system to find something to replace this. This is actually a variable. It's a placeholder. Okay? It's kind of like, give me something in the extension of P. Or give me something in the intension of P, of course, semantically. So that's the type of question you can ask the system at this layer. Okay? Very simple. Then that's it. That's the grammar. Okay. So the language itself is called Narcisse. Later we will refer to it. And also is extended incrementally layer by layer. So this is the version 1. It's the simplest form. And later we'll see this become more and more and more complicated to the level that hopefully it will capture all type of knowledge you want to put into the system. But we'll have to start somewhere. Now, this is a summary of the representation part. Now you see how to write things, put it into the system. Now, how about reasoning? There are 3 major groups of rules. Okay. The first group, and first, where to start? Right? The actual start is what you gave to the system, which also is what we here call actual experience. We distinguish this from the previous idealized experience. Okay? Idealized experience is something like this. Okay, that's what we have seen. The actual experience will add a truth value to each of them. Everything is true to a degree, except the questions. The questions are also part of the experience. Okay? So anyway, you just feed a sequence of this into the system. That's where everything starts. Initially, you can assume within the system, there is nothing. The memory is blank. Okay, everything comes in experience as a stream of sentence when we call it a stream, not a set, because here later you'll see order actually matters. And not only that, timing also matters. Okay? So if something gets into the system, and here the meaning of those terms and the truth value explained according to the previous definition about the truth and the meaning, and based on the system's experience and the knowledge derived from the experience as introduced before. That thing is called the so-called experience-grounded semantics. And then now you see that given this situation, everything is subjective, uncertain, and change over time. Subjective means that the system's opinion is completely determined by its own experience. Okay. Uncertain means that everything here is a matter of degree. You don't have absolute truth. Confidence never reach 1. Okay. Even though frequency can be 1 or there or something in between. Confidence, you can never 100% confident. And also, this is also matters. Experience is open-ended. Okay, in ours, we assume there is always a future, there is always possible future experience. So this is also a major difference between this model and the traditional model theory, which against a fixed model, you decide truth value and the meaning. Okay. And here, everything flows in time. Then the inference rules are also justified according to this new semantics. It's not traditional model theoretic semantics. And this is also an interesting point. The inference rules in ours is both syntactic and semantic. What that mean? Last time I mentioned the Chinese room argument, right? One argument there, actually what John Searle argues is if you have a rule, like let's just use the syllogistic rule, because according to him, it doesn't make any difference here. Okay, so of course there are some truth value that's ignore that kind of detail. You give the system this, the system derive this. John Searle argued that if you're in a computer system, that's the only thing you can do, meaning that you can recognize its shape. For example, you can see this and this are the same. Okay, this is a special symbol, and these are the allowed characters or identifiers you can use. And you have no idea about the meaning. For example, this S may actually represent water, and this may actually represent the liquid as in my previous example. Okay, or this can actually represent the raven, and this can represent bird in my other example. John Searle's argument is you have no idea what you're talking about. Okay, you can do this reasoning, yeah, according to your rule. You have no access to the meaning. That's not completely true in NARS anymore. There are some truths. Yes, NARS clearly recognize the shape. Okay, this two have different shape, and this two have the same shape, so it will work accordingly. But with respect to meaning, here meaning does not refer to something in outside world anymore. Okay, the meaning of this term depends on its relation with the other term, including this relation. So as soon as this is one premise we use in this step of inference, the meaning of M and S are already involved. You're using one of its extension. Symmetrically, you're using this one's intension. Okay, the same thing for the conclusion, which also means that for this two statement to be used together, their shared term also guarantees the meaning of these two sentences are related to each other. This is actually a big deal in logic. Okay? In proposition logic, I have mentioned the truth value table. For example, a trouble, and yeah, in proposition logic, this is called implication, right? It's not the same as my inheritance. Let's just use some special. This is defined to be what? To be equivalent to, right? You know this. So the truth value of this is completely determined by the truth value of this two. On the other hand, this one is intuitively interpreted as if then. Not only that, many so-called causal relation is represented in this way. But it causes a lot of trouble because according to this definition, you can use an arbitrary P and arbitrary Q to form such a statement. Some of them will be true, even though it's completely meaningless because these two P's are not related to each other. For example, 1 plus 1 equal to 3 implies 2 multiply 2 equal to 4. This is a true sentence. Everyone will say that's ridiculous, okay? This is so-called the paradox of implication in first order in propositional logic, which is inherited by first order predicate calculus. And there is a whole branch of logic called relevance logic. They try to get rid of this. Okay, this you cannot say this is wrong. It just doesn't make sense. Why? They try to fix it with propositional logic. But few people realize that that problem does not even exist in Aristotle's term logic, because this syllogistic format of the rule already required a common term, which according to experience-grounded semantics, guaranteed these two are related. Whether this is right or wrong, that's a separate story. They will be related, and also this one, this one, this one, and this one, they will all be semantically related. Okay, so this is another concrete argument against John Searle's Chinese room argument. It's not just philosophically wrong, it's also logically wrong, because he assumes another type of logic. So this is what I mean. And how about the truth value? You see, I said that this one is not built according to the old traditional truth value truth table, but of course there is truth value involved. So let's just take the simplest case. If this is true to a degree, this is true to a degree. Of course, there should be a different degree. Then this, you can still do it, but that will also be true to a degree. And this numbers is determined both by these numbers and also by this combination. Okay, later we will see how that is established in non-axiomatic logic. That's, of course, a key component. But the basic idea I can tell you, the first thing I tried, as many people can guess, is to try to derive it from probability theory. Then I realized it's not going to work. Okay. And then what I have done actually is to extend Boolean algebra from binary to multi-value. Okay? And the detail is actually described in the book. This is also not completely invented by myself. There are some other people with similar need. Say, for example, some type of fuzzy logic, some other kind of calculus. They need something, not just 0 and 1, but between 0 and 1. But they still need the basic operation, the logical relation, and, or, and not. Well, how to do that? Okay, a common treatment. Actually, it looks also pretty natural. Negation is the complement. So if this is true to say 70%, then it's false to 30%, add together to 1. The same as the probability, but interpreted differently. And is multiplication. Also, as probability theory under the assumption of independence. Okay, and actually, given the relationship among the three from this two, the OR relation is uniquely determined, okay, which is given by this more complicated formula, which if you only have two A or B, okay, actually the calculation is simpler, is A plus B minus AB. Also the same thing as in probability theory under the assumption of independence. Anyway, this is how we are going to actually build the truth value, a sum of the truth value functions. So that's kind of like a general summary, and then let's go into the three groups of rules. The first group is called the local rule. It's special in the sense that you don't really derive anything, okay? But you need that kind of thing for this type of logic. You don't need them in traditional logic. The first one is called revision. What is revision? What if you have the two premises actually identical in content? This is what? In general, you can say this is a contradiction or inconsistency, okay? And that's, of course, not allowed in traditional theory because each of them, there can only be one truth value. You cannot have two. If you have two, they must be identical, okay? But according to experience-grounded semantics, this is a summary of part of your experience. This is a summary of another part of your experience. Or you can think it as the information you collected from different sources about the same thing. And you can get different people's opinion, or you can check different database, whatever. They are not guaranteed to be the same, okay? According to the assumption of distributed knowledge and resource. Then what you can do about it? You need to deal with it. You cannot just report error because this actually is a normal situation for this kind of system. This is how learning happens. New evidence will modify your previous belief according to whether it will add more evidence in the positive side or in the negative side. So this is a normal situation. But if you think it in that way, actually the solution is pretty obvious. As far as you can assume the evidence come from different sources, then they simply accumulate, okay? So that's why if you check the truth function, which is explained in detail in a book somewhere, it's a simple, it's just addition, okay? What's that? That's the positive evidence of this one and the positive evidence of this one will be added together to become the positive evidence of this. And similarly for the negative evidence and for the total. Okay, so they will just simply be added together. So this is nothing but the sigma. For the positive and the negative and the total, then of course you can use that to calculate the truth value using the relationship like this ratio is frequency and confidence is from this one and so on. Okay. The intuitive feature also is not hard to understand. Okay. So this is just addition. Frequency, as you can guess, this one is a compromise of this two. This will be somewhere in between. It's a weighted average. Okay, it will not be too extreme for either of them. And the weight value actually is provided by the confidence, not directly. Okay, you can see the formula, but it is still a weight. So more evidence, of course, is a heavier weight. And then finally, this confidence level will be higher than both because this is the total. Right? This is part, you put them together, and this will be larger. Again, for the current discussion, we don't want to go into the mathematical detail. We don't have the time, okay? But that's the idea. So this is the revision rule, which is unique in the system and is crucial for its learning function. Another thing is called a choice rule. And this one also, why is called the local rule? Because it does not really produce anything new. It just kind of like modify the truth values or accumulate the truth values. Or choice rule, on the other hand, is also, as the name suggests, it's a choice. About what? About how to answer a given question. Say, for example, the first type of question we said is something like this. Okay. It's a yes/no question. And how to answer this, of course, it can be answered by a statement of this form that they match. Okay, so you use this to answer that. But what if you have more than one? Because NARS is not fully consistent, and you may have this scenario, and in some situation later we'll see, they cannot be merged using the revision rule because they are based on overlapping evidence. So if that's the case, then which one you should pick? Very simple. Which one is based on more evidence? I asked two people the same question, okay? One say yes, no, the other one say no. The yes answer is based on 500 observation. The no answer is based on 3 observations. Of course, I will go with 500. Okay? It's not because it's more correct. It's because adaptive system means that prefer more evidence.
What if some of the evidence is more recent than the previous?
Good question. That will be handled in a more complicated way in the future. For now, there is no time involved. Okay, we just have the amount. Say who have more evidence, that's the one that gave me the final decision. So that's E there. How about this question, the WH question? In this case, we not only have 2 different truth values, we actually have 2 different candidates to be used. For example, you're looking for S as a property or intension. Intention very often is interpreted as a property. Okay, now I have 2 of them. And if I have to make a choice, which one is a better one? If we don't think about anything about time and relevance and so on, only based on truth value, you'll see that in this case, we actually need to combine these 2 factors together. On one hand, we prefer a high frequency because that's more true. On the other hand, we also prefer higher confidence because it's more certain. Okay, so if this is higher than this is higher than this, that's simple, clearly we pick this one. The tricky part is this one is higher, but this one is lower. Then which one do you prefer? This is a long story, but the short answer is we use a formula to summarize them into one number, which is called expectation of future frequency, which is given by this formula. Okay, there is a long story behind this one, and also related to some traditional work, which is explained in the book. I have to skip, otherwise I'm running out of time again. So that's what we call the local rule. Revision and choice for the judgment and question respectively. But the major part of this, of course, is the stochastic rule, which is called forward reasoning or forward rule. Traditionally in AI, a so-called forward reasoning is exactly the pattern I have here, is you have 2 pieces of knowledge and you want to derive a 3rd piece or to derive new knowledge. Or we can say this is reasoning in the default sense. Okay, so in this model, as we have already said, is a stochastic, which means that each of the premise is between 2 terms. And also is required that there must be one in common. Now you think about it. How many possibilities are there? there are actually only three possibilities. Logically speaking. One is the shared term is the subject of one and the predicate of the other. Then you have a chain. It's kind of like two links in this way. Okay. Another situation is the shared term is a common subject. Then you have this. But finally, you can guess. A common term is the common predicate. Then you have this. Okay? Only this three possible combination if you want one common term. And they happen to correspond to what? To deduction, induction, and abduction. Okay. That's something I'm very proud of this model. It naturally fit into the traditional logic study. And as you can guess, that's what I put as in a function name for the truth value function. So this combination is deduction, this is abduction, this is induction. What is this one? This one is called X amplification. It's not very often used in the study, but if you think about it, it also makes sense. This is the other way around of deduction. Okay, so the combination is the same, but in the conclusion, I use this as a subject, and this is the predicate. Okay, so instead of get a transitive conclusion at 10 in a row. On the other hand, this one, each of them actually produce a pair of conclusion. You see, it's symmetric, right? So which one is the first premise, which one is the second, it doesn't really matter as far as this combination goes. Okay, so if you can derive something in this way, you can also derive something in this way. So induction and abduction produce paired conclusion, and deduction and exemplification produce something in opposite direction. That explains why here we actually have 4 different combinations, because you also take the direction into consideration, even though according to that logic, there are only 3 combinations. Then we are the function, so the shape become pretty clear. And one premise have one truth value, the other one have another one. How are those? Of course, different type of inference have different truth value function, of course. But how are they decided? We don't have the time for that. I know there will be a lot of questions. It's explained in the book. The basic principle, as I said, is use extended Boolean algebra, which is given in this form. That is, I first analyze all the related factors as the binary. So what if this F and C are nothing but 1 and 0? Then in that situation, what I can say about my conclusion, according to the semantics I provided. Okay, I can tell you that this basically tells you deduction is nothing but a generalized form of transitivity. The extreme case is this is absolutely true, this is also absolutely true, then this is absolutely true. Okay. And induction and abduction, actually they correspond to the 2 forms. I hope you still remember the diagram I draw here about evidence. These 2 perfectly match the extensional and intentional evidence. So if you have something which is both S and P, is positive evidence for both conclusions. If it's S but not P, is negative evidence for this direction. but have nothing to do with the other way around. Okay? Abduction is symmetric. So again, I don't have the time to detail, but this is where it comes from. So under what situation you have positive evidence, in what situation you have negative evidence, if all the variables are taken to be Boolean. Then what? Then I just use the non-Boolean version, the extended version, and not. I just showed you before. Okay. I also use the relationship between truth value and the amount of evidence, which will give you this column of formula that's actually in the code that calculate the truth value. Okay. This is the theoretical part, which will also cover exemplification. It's less interesting form. So yeah, this is a long story, but you do need to read the book to actually understand what's going on. But I hope you get the basic idea. And finally, the last group is what's called backward reasoning. Backward reasoning in traditional AI, sometimes also called backward chaining. I don't use that because I don't really form a chain. But the idea is this. The format is similar. You have two premises, you get a conclusion. Here, the difference is one of them is a question. Okay, this is a question. This one is what we call a belief, is something already taken by the system. Then what do you get? You get a derived question. But of course, here we also need to satisfy the syllogistic requirement by using a shared term. Otherwise, nothing can be derived. Okay? So in this kind of situation, what you can derive clearly is a relationship between A and D in both directions. And they are questions. What's that supposed to mean? This is a type of reasoning we do a lot when we solve a complicated problem. We start from the question or the target. We see, if I want to get here, what I need to arrive first. So this basically say that if I can answer this one, then from this one and this one, I can get an answer for this one. Okay, the same thing here, even though the combinations are different. So the basic idea is from a question and a judgment, I can get another question if and only if the answer for this one, which is another judgment, with this judgment will derive an answer for the original one by forward reasoning. Okay, so backward reasoning, that's where the name comes from. That's you're using the semi-infinite rule, but you're going backwards, which will work out if eventually you touch the bottom, you answer this one, you answer the derived question, then it will allow you to go back. It's kind of like recursion. Okay, you're reducing a problem into a sub-problem or a simplified problem until you have a solution to that, then you go back to answer the original one. And here, you can not only do it in one direction, you need to do it both because this is the direction where you actually do a truth value calculation. And because question has no truth value, it just you want to know it. So backward reasoning is a little bit more complicated because it's like go back and forth. Again, the details are in the book. And this lecture is more tense because it touches a whole bunch of traditional problems, which we don't have the time, but I want to list them there. And also I have links to where the problem is explained in some source, sometimes like Wikipedia and so on. I will briefly tell you how NARS answer each of them. Okay, Hume's problem of induction, actually we discussed it last time. Okay. The problem is induction is using the past experience. If you use it to answer future questions, you cannot guarantee truth. And that's what Hume argued, I think, convincingly. Here, the solution actually, some people will say that's cheating. Okay, to me, that's the right way to do, is change the definition of truth value. Instead of talking about the world, you just talk about what you know. Okay? So induction in this case is justified in the same way as deduction, because the conclusion's truth value doesn't really talk about the future. It talk about the past. Talk about from the given evidence, how much I can say, how much I believe this thing. So we can give it justification. Humboldt's confirmation paradox, I don't know whether you have heard about it, it's very interesting. Sometimes it's also called Relevance paradox. He's talking about how to modify traditional logic to add the idea that evidence can change your opinion. Like, for example, it's called Relevance paradox because the original form is about if something is relevant, then it must be black. Okay? This sounds trivial. I will ignore the details, but that's the basic idea. But logically, this one everyone knows is equivalent to if it's not black, then it cannot be relevant. In traditional logic, everything is either true or false, and this two will have the same truth value. If you want to modify it, you will allow it to be a matter of degree. Then what is positive evidence? Positive evidence traditionally is taken to be if something is relevant, it's also black. It should make you believe higher about the relevance of black because that's a positive case. Perfect, but think about this. If something is not black and not relevant, it should, for the same reason, it should make you believe that's better. Okay, let's use, how about this example? This is not black and also not relevant, clearly. It should increase your truth of degree of belief about this one. But this one are the same thing. So when you see this, you should believe stronger that relevance are not black. That's ridiculous. Okay. Every normal people say that's ridiculous, except logicians. They say you have to accept that because there's two equivalent. Okay. What's the solution in NARS? In NARS, these two are not equivalent. Okay. They have the same negative evidence, but they have different positive evidence. So we don't have this problem. Again, we have a paper on that if you were interested in that. Winston's selection task, I don't know if some of you are from psychology department, you should know this because this is one of the best known experiment in cognitive psychology. Okay. So I show you 4 cards like this. Then I tell you a rule. Say that each card has a number on one side and a color on the other side. Which card you should be turned to test the idea that the card show an even number on one side, and then its opposite is red. You can think about it, but I can tell you the conclusion, okay? According to logic, there is one solution. According to almost everyone else, this experiment has been done millions of times. People's choice is different from logic. Okay? This is widely used as evidence that people's mind, people's reasoning is irrational. But my interpretation is different. I say people are right, the logic is wrong, because the logic they're using is first order predicate calculus, which does not take positive evidence into consideration when they decide truth value. But NARS does, so we don't have that issue. Again, we have a paper on that. Paradox of material implication I already mentioned. Okay, that's about the relevance logic saying 1 + 1 = 3 implies 2 multiplied 2 = 4. Why we don't have that trouble? Again, that's a problem in predicate calculus, not in logic. Limitation of term logic, I already said something. Why people said term logic is already dead? Because indeed it's not the expression power and inference power are weak compared to first order predicate calculus. But it can be extended. Okay, that's what we did. And also some other people also tried similar things. Actually, it can be extended to the level of first order predicate calculus and even beyond. What I'm interested in is in the beyond part. That is, if we really want to do, my major reason is not just to, reevaluate Aristotle. My major motivation is to do something other than deduction. I find to do it in term logic, you can see here, is much more elegant than to do it in predicate calculus. So deduction, abduction, induction are very naturally and elegantly organized into the same picture. And term logic can be extended to get rid of the limitation people have been talking about. Default reasoning is about change truth value, change degree of belief, which we have already seen in the revision rule. Conjunction fallacy is another well-known example used to show people's irrationality, which is very interesting. I'm sure we will need to discuss it, but not today. We run out of time. So this is about the meaning of a concept. Okay, we don't have that issue in ours, or our conclusion is closer to humans' intuition than to classical reasoning model. And randomness, fuzziness, I think I have already touched that a little bit. So the truth value here actually summarizes different type of uncertainty. Sometimes it's similar to randomness. Sometimes actually is closer to fuzziness. This is especially the situation when you're talking about intentional factor. Actually, the same thing for this conjunction fallacy. Traditional logic focus on extension. If you take both extension and intention into consideration, then many problems get different answers. So I hope we can have time in the future to go back to some of those issues. But if you're interested, you can take a look. And this is suggested reading for today. And that's all. And finally, announcement. We don't have a lecture next week, which is already somewhere mentioned in the schedule, I think. Is that that day is listed as a self-study day because there will be some activity happening here. And also we think we can use that time, ask everyone to begin to think about what you want to do for your course project or something. Patrick, do you want to say a few about that?
Yes. Yes. Maybe I should share my screen.
Yeah, you can, but I will show people first that this is a schedule. This is today. Okay, our next lecture will be in 2 weeks. Okay, not next week. So not next week, don't come here. Instead, working at home. Mhm. You can share your screen.
Camera. Yes, so I have also put the link into the chat. Essentially, I have created a entry here. Since there is no lecture next week, we thought it would be best to take this as an opportunity to get discussions about Quest projects going. And of course, there will be many possibilities here. But overall, there will be two major categories, since not everyone in this course has a technical background. So there will be software projects, and there will essentially be writing projects, depending on what is preferred. And so what we suggest here is to start thinking about potential writing or software projects related to this course. And yes, and to get the discussion going, to use this discussion board, which we will also send out via email, to come up with a title of the project and an overview about what could potentially be done in it. So that's the idea here. And maybe I will take this opportunity to show you what we have, for instance, done in the past with this non-axiomatic reasoning system. Let's see if this works. But it's one window is in the way. Just to give you an illustration, of course, for this course, we don't expect complex projects to be performed, because what I will show you now were projects which we have been working on for a longer time period, at least a year for each. For instance, here, this particular case is a traffic surveillance system where we use the reasoning system to identify anomalies in a smart city scenario, but with the special property that essentially that there is real-time learning part of this picture. Essentially, the system learns what parts of the scene are usually used by cars and by pedestrians, and also the system learns how the objects behave. For instance, here we see a prediction. Maybe I can go from here. Prediction error, which indicates that the system thinks that this object will appear here at this location in the future. So it builds on understanding about how objects move in the scene, depending on which object it sees. And the idea here is to combine this with anomalies. But if we take anomalies simply as things which happen, as events which happen, which have not been predicted by the system, then there would be always anomalies, like some person coming in from there or there, which the system could not have predicted. So it would be anomalous. So the idea is then to filter out many of the anomalies by simply saying, we also want to include some background knowledge where the operator, for instance, can specify, I'm only interested in anomalies related to like the locations of pedestrians. And then, for instance, the system would say, yes, I have some cases where pedestrians were walking on an area which is typically occupied by cars. For instance, to give one example of traffic anomalies, this is essentially then used to detect cases like jaywalking. And yes, we also see other anomalies, like when cars come particularly close to pedestrians, which might be related to which can be relevant for safety considerations, like if in a certain intersection or so, if it's often happening that cars close to pedestrians with a high speed, then maybe there needs to be something improved in the intersection. Just to give an example. So this is one project we did, and more recently we did one with NASA Jet Propulsion Laboratory. So previous was with Cisco systems, and this is with NASA Jet Propulsion Laboratory, where we essentially used the system to assist a first responder vehicle, or to assist the first responder who is driving the vehicle. And assisting here means multiple things. One is to warn the first responders when there are potential dangers. So, for instance, in this scene, we see there is a vehicle approaching which does not stop in the intersection, and the reasoning system notices this. So also here, temporal learning is important because the system needs to learn under what conditions cars tend to stop in the intersection. So for instance, if we look at the traffic light color, clearly it's dependent on the traffic light colors, the color whether cars typically will stop or not. So if the system notices, in this case, that the car is not slowing down, even though it should in this case. So it's giving this warning message, which in this case is safety relevant. But we can also do other things like learning what are typical speeds of cars at particular intersections, because this is really dependent on a lot of factors. It's not just about speed limit, because for many road segments, it's the case that people drive according to their own safety estimates. Sometimes this can be above speed limit. So it's good if the system can watch the scene and notice what are typical speeds for each lane, so that we can then again detect corner cases, like there's a car here which goes particularly fast in this lane compared to typical speeds for this lane, and that's close to the shoulder where the first responder vehicle is parked. So it would be good if we could detect this. This is just one of the examples. This is mostly combining some learning aspect with some background knowledge, and more recently we have also moved into robotics, where we essentially show that real-time learning can be combined with background knowledge to build essentially autonomous robots. And so the idea is to essentially make them more robust to certain disturbances in the environment by allowing it to learn missing knowledge from observation. So that's the idea. So essentially, we specify only the most relevant information. No, that's not put correctly. What I wanted to say is we specify only the mission-related information, like what it has to carry out, but we don't mention all the details about how this task can actually be performed. So, for instance, this robot, what it currently can do, it can, for instance, learn how to avoid obstacles, even when we don't tell it how to do this. It can essentially pick it up from observation of how it can essentially get around in the environment without getting stuck. And it can also correlate events it gets from multiple modalities. This particular robot has multiple sensors on board. One is a LiDAR sensor, which allows it to map its environment. It has a camera with a depth camera even, so it can also, which we can utilize to detect objects and also the distance relative to the robot. And with this combined, it can then, for instance, correlate object detections from a vision model and correlate them with the location estimate. And why is this useful? It's useful because it means the reasoning system simply via an inductive inference is able to remember where certain objects are perceived in the environment and also how they are perceived in relation to each other. Like if the system sees a fridge, then it's not unusual that there will be a microwave somewhere around. So it will essentially build expectations about objects, how they are positioned relative to each other, and also where they essentially can be seen, so that it can later revisit the location. So in this particular task, for instance, we specify that it should bring a bottle to the human operator. So the idea is then it has to find the bottle. But ideally, if it has seen the human before, it should also remember where the human is, and then bring the bottle to the human without having to search for him if it already knows where the human is. So just to give an example. So these are some of the projects we have tried with this reasoning system, but of course there are many other possibilities. For instance, also comparisons with reinforcement learning. Here we have essentially taken a few common domains which are tried with traditional reinforcement learning techniques, and we have simply tried whether the procedural learning abilities of the reasoner are sufficient to learn similar tasks, like learn to play Pong, learn to get around in a grid world environment, and so on. So these are just a few examples of things one can do with this project already now, even though it's still early stage, I would say. But this might give you some inspirations about what directions course projects here could potentially take. Yes.
Maybe somewhat interesting, because I know that at least the lectures so far have been pretty, been going into like Norse theory or like non-axiomatic logic. I was thinking maybe it would be interesting to talk a little bit more about how you actually apply ONA for like what are the tricks, to convert, for example, numbers into terms, or like what are the tricks needed to get something like this to work, as you're showing on the screen?
Mm-hmm. That's a good point. How much time do you think we have in case?
I think we should take a break now. Then we just like normal discussion time. We can continue this in the discussion time.
Mm-hmm.
So people who want to leave can leave, and want to stay can stay.
Oh yes.
The same for the online people.
Mm-hmm. In this case, so what I will certainly do is to post the relevant materials of how to use this system. But of course, for this course, since it's a AGI course, if someone has another system in mind, that there are also other AGI projects out there, of course, which would also qualify for this project. And so we don't want to restrict the possibilities here. But of course, we will also especially post the materials of how to use NAS in particular situations, how it can be used on the computer, essentially. Yes, then I guess we can take a break now.